morning, everybody. In today's video, I wanted to talk about what an ideal is in the context of ring theory, and and to kind of explain where the definition of the ideal comes from and why we construct it as such, as you will see in this video. So why don't we start with the boring part? I will write down the definition of what an ideal is in ring theory, and then we can delve into where exactly this definition comes from. So let's start with a ring R, and then what we'll do here is we take some subset, which we'll call I, of our ring, and this is an ideal if it respects the two following criteria. So the first one is that I is a normal subgroup with respect. Ooh, I forgot to write group. Hold on. Let's erase this. Is a normal subgroup. There we go. Of R with respect to its addition. The second criterion is that for all R, for every element of our ring, if we take that element and we multiply it by I, this set is entirely contained within I. Likewise, if we multiply on the other side, if we multiply on the right, the set is also entirely contained within I. And so these two criteria are basically the two criteria that define an ideal. And well, okay, so where does the first one come from and where does the second one come from? The first one comes from, well, let's recall back from our group theory class. Recall from group theory that we can construct what is called the quotient group. And the way this works is we would take a group G, and then we would also take a subgroup, let's call it H, a normal subgroup of G. And with these two, with first the group and then one of its normal subgroups, we can construct G mod H. And G mod H is what we call the quotient group. Now, it is the quotient group. Well, what is the quotient group exactly? It's the group of all the cosets of H endowed with a certain operation. Yeah, it forms a group. It forms exactly that. And so we want to do the same thing in rings. We want to have a quotient ring. But it doesn't suffice that I, our ideal, or the set that we want to be an ideal, it doesn't suffice that this is only a normal subgroup. We have to endow it with a second property. And, well, yeah, of course, the second property seems to come out of nowhere. And so I will explain where the second property comes from and why we have it as a property. So let's start by taking some element in A in I, and then we'll take another element, call it R, which is not in I. Of course, this element is in the ring R. So we have these two elements, and if we were to say, I don't know, construct R mod I, then we would have A in I would mean, so in R mod I, we would have I plus A. This is simply equal to I. This is an element of R mod I. And we would also have some element I plus R, another coset I plus R. And this is also in our quotient ring. With these two elements defined, well, why don't we multiply these two elements and see what happens? I plus A times I plus R. And well, the most natural way to multiply these two together is to simply multiply their representatives. So, in other words, we would multiply this as I plus A times R, like so. That's a very natural way of going about it, but this poses a few problems. It poses a few problems. So let's analyze this equality. Let's see what it tells us. On the left-hand side, I plus A, well, this is just simply equal to I. But I in the quotient ring is the zero element. It's the neutral element with respect to addition. And then on the other hand, well, we have something that's I plus R is something that is not equal. It's not equal to the zero element. Okay, well, anything times zero naturally is going to be zero. So this is just zero in R mod I. Okay, let's look at the right-hand side now. What do we have on the right-hand side? We have A times R. What is that? What the hell is that? A times R. Well, the thing is, we wouldn't know what A times R is. Not necessarily, unless we look at our second criteria here. So the only way we can have equality, the only way I plus AR is equal to our zero element is if this is only true if AR is in our ideal. But AR in our ideal, oh, we've seen that before. This is exactly this. So these two things are the same. And so this is exactly the motivation for the second criterion. The second criterion here in our ring. Because if we were to take any element in our ring and then multiply it by our set here, it would have to still be contained within this set, or else this multiplication doesn't make sense, and we would have 0 is equal to something that's not 0, which is clearly not something that we want. And so yeah, I mean, that's basically the motivation for the two criteria that define an ideal. So to resume, the first one is that I has to be a normal subgroup with respect to addition, a normal subgroup of our ring R. And the second one is that, well, we take any element of our ring and we multiply it by our set I, and the resulting set is entirely contained within I. And same thing if we multiply it on the right. And we just saw that the reason for the second criterion has to do exactly with this equality here, because this is only equal if AR is in I, which is the second criterion. So that's basically it. Thank you everyone for watching. I'll catch you in the next video.